Hey guys, Mr. Wood back for another lesson. We're going to finish chapter 5 here. So again, try and not make it as long. Try 15 minutes or so, maybe a little bit more. But of course, we've got to start off with jokes. And here we go. What do you get when you cross a bank with a skunk? What do you get if you cross a bank with a skunk? Dollars and cents. Dollars and cents. There you go. Okay, so today I'm going to finish chapter 5. I'm going to go through some stuff, kind of, again, trying to skip the thing, go through the things you really need to know. And I'll review this on Monday and Tuesday, and we'll be done with 5, and we're going to move into chapter 6. We kind of have a weird schedule the next couple weeks. So here we go. Okay, we already have talked about this slide, so let me go through. We talked about this. We've done that problem. We talked about kinetic molecular theory. We went through that. And this is where we left off. We talked about the Maxwell-Boltzmann diagrams. Note where the peak is. Where the peak is the average, and that's what temperature is. Temperature is an average of all the kinetic energy of the it's the average kinetic energy of the molecules in a sample. That's what temperature is defined as. Remember what we said too. We said if we have two different gases at the same temperature, they have the same kinetic energy. If they're at the same temperature, they have the same kinetic energy. But if they're at the same temperature, the one that's smaller by molar mass would be moving faster. So 2 items there. Okay, and this is really, again, a page I'm going to skip. If you guys take chemistry in college, you guys will use this. But really, this goes back to what we were just talking about. That is, the molar mass, as the molecular weight increases, the velocity decreases. So really, we talked about this already. And again, this calculation is one that's not going to be in our class. It's not going to be on the AP test, but it could be in your first year of college chemistry. So as the molecular weight goes up, the velocity goes down. Okay, and I'm actually going to skip this page too because it's connected to that last page. And then here's another thing, and this is a small minor point, but the word diffusion. We're going to have diffusion here now, and in a minute, effusion. Diffusion is a rate at which a gas travels from high to low concentration through another gas. So that's the definition of diffusion. Lighter gas molecules have a higher average velocity, same exact principle. The smaller a molecule is, the faster it moves. Therefore, diffuses faster. And if you look at that, what I've got there in the box, if I have NH3, which has a molar mass of 17 on the left, and on the right I have HCl, which has a molar mass of 36.5. So HCl weighs twice what NH3. Well, when I put those two gases in that tube, they react making ammonium chloride. That's that white ring, but notice it's closer to the HCl. The reason for that is because the NH3 moves faster because it's smaller. So principles, the definition is something new. You should note that. Diffusion, the rate at which gas travels from high to low concentration, but the principle is the same. The lighter molecule will travel faster than the larger molecule. Okay, and then effusion, kind of this, it's a little bit different. The rate at which a gas travels through a tiny hole into an evacuated chamber. Kind of a strange thing. They actually use this. I'll show you here in a slide. This is how the word they use in chemistry, this is how they enrich uranium. They make uranium where they find the uranium that can be used for nuclear energy or nuclear weapon. Because well, I'll talk about it here in a second, but they use this principle of effusion. But so this is what effusion is, the definition. So it's a little bit different than diffusion. These are not big points in this chapter, not important points. The rate at which a gas travels through a tiny hole into an evacuated chamber, and heavier gases effuse slower. So really, it's the same principle. So the smaller gas will effuse faster than the smaller gas will effuse and diffuse faster than the larger gas. Okay, and this again is something that we used to do years ago in AP chemistry. We're not going to do it this year. It's not going to be on the AP test, our test, but maybe if you take chemistry in college, same thing. So again, skipping stuff that we're not going to need to go. Here is what I was talking about. Again, this is just more for your information. U-238, uranium-238, of all the uranium that's mined on the planet, like a large percentage, I don't remember the number, but like 98, 99%. Let me just finish this video, Zion. If you come back in like 5 or 10 minutes, okay? Over 95% of all the uranium that's mined is uranium-238, but the problem with that is that it's not fissionable. It cannot be used to create nuclear energy. But uranium-235, which is mined at like 1%, it can be used in nuclear energy or in a nuclear weapon. And so they use that principle of effusion. And eventually, when you have a mixture of uranium, you get enriched a higher concentration of uranium-235. And they have these big, these big buildings to do this in. And this is how the United States was kind of thinking Iran had a nuclear weapon. So again, nothing you need to know, kind of for your information. Non-ideal gases, we've talked about this. A non-ideal gas is something that is, so this is when two gases are going to interact. They're going to have a push, a force on each other. So gases tend to behave most ideally at high temperatures and low pressures. If these conditions are not met, corrections in the ideal gas law equation must be factored in, which I'm going to show you on the next slide, but we're not going to need to know that formula. But you do need to know what is ideal gas behavior and non-ideal gas behavior. And we talked about that already. Non-ideal gas behavior is going to be at high pressures, low temperatures, and polar molecules. Okay, and then this is the adjustment. Again, this is something that you could get into beyond our class where they actually calculate when it's a non-ideal gas behavior. And it's not a difficult calculation, but it's nothing we need to know how to do. Okay, and again, I'm just skipping through stuff. Okay, last thing. Like I said, of all the lessons I've had, this is fairly short. But this one, there's two environmental issues, environmental effects that involve gases, and I'm going to put this on our test as extra credit, one of these two, and you're just going to have to just do some memorization and a short description. This is one possibility. This is called photochemical smog, and so this is produced, it's initiated by sunlight. Okay, so let me just real quick here minimize the screen. So again, this one, and I'm going to be talking about sulfur and coal here in a second too. And one of these two is going to be a little bit of extra credit. Now, the key thing on this first one, photochemical smog, is when we run our cars or buses run, this is what happens is they take N2 from the air and they take O2, and what you get off is you get off NO. So this just occurs in automobile engines. Okay, so what happens here is the production of these nitrogen oxides. Could be NO or NO2 or N2O3. Okay, now if we go back to this, so we get this nitrogen oxygen compound. And again, all you're going to need to do to get points is one of these two, like I said, are going to be on the next test. And I'll give you extra credit for it. So if you don't care about extra credit, don't worry about it. But so you produce the NO2. And notice that acting as a catalyst there is sunlight. See that it says gasoline engines produce NO. That's what I tried to talk about behind me, mainly NO2. Well, the NO2 then with sunlight, that's why it's called photochemical smog, it dissociates the NO2 and you can see the series of reactions. So what I'll expect you to do on the test, if the one I want you to talk about is photochemical smog, is what I've got behind me, and then you're just going to show this series of reactions. So the NO2, again, catalyzed by the sunlight, breaks down into NO and O, and then the O breaks down, or the O then combines with O2 in the air and makes ozone. And ozone is something that is not good for our lungs. And you can see what it does to our lungs. It's difficult to see, but the lower left-hand picture. And then in number 2, the oxygen, then that lone oxygen combines with water to make 2OH, and then the OH combines with NO2 to make nitric acid. So O3 and HNO3. So O3 is called ozone, and HNO3 is nitric acid, are photochemical smog, a form of pollution stimulated by sunlight. Photochemical smog peaks in late afternoon and then decrease. And this is a problem in the summer. It is not a problem in the winter. And if you think about when you drive around, you'll see sometimes on those big placards, don't mow your grass today, especially because it's catalyzed by sunlight, and that's more of an issue in the summer. Okay, so that is one possibility. And the other possibility is this reaction right here. Sulfur is a minor part of coal. And when the coal is burned, and there's different grades of coal, but if this is, again, one of these two issues, this is what this is involved. This is involved in making acid rain. So you just write out the series of reactions, but the sulfur is burned when coal is produced, and it makes SO2, and then the SO2 again combines with oxygen to make 2SO3, and then that SO3 combines with water in the air and makes sulfuric acid. Makes acid rain. More of a problem in highly industrialized areas. Colorado, not a problem, but like in the Northeast United States and Europe, it's a bit of a problem. Some statues, even I could show you pictures of statues that start to deteriorate because of this. Lakes and rivers get a higher level of acidity than they should have. But to help with that problem, they use these things called scrubbers. And so you can see the reaction. If you put calcium carbonate plus heat, so calcium carbonate is chalk. So you heat chalk, you get calcium oxide, a solid, and CO2. Well, if you take that calcium oxide and you put it in the smokestack, it combines with the SO2, which removes the SO2, which thus is going to remove a key part of this chain. So the SO2 will be removed. And so this idea of scrubbing is a way to reduce this effect. This is about acid rain. And so producing acid rain. This, again, you would write out the series of steps, just a brief explanation. And I'm going to give you some extra credit, either for this or the photochemical smog. I just had in my notes that in 1970s, a lot of the factories produced SO2, so the EPA, the Environmental Protection Agency, required a scrubber, as I just tried to describe to you, the Clean Air Act of 1980. And sulfuric acid, by the way, is the acid in car batteries. But the amount now of calcium sulfite that is produced is 300 billion tons of CaSO3, calcium sulfite, a year. So if you want to become wealthy, if you can figure out what to do with that CaSO3, you'd become wealthy. Excel has to pay a company to put calcium sulfite in a landfill. There's about a ton for every American calcium sulfite produced. Okay, so that is it. We're done with chapter 5. Guys, be studying, and we're going to move into chapter 6. We'll do a little review on Monday, Tuesday, and we're going to move into chapter 6. Talk to you later. Have a good weekend.